Now we can see basic signal operations. Basic signal operations performed on dependent variables. Dependent variables is nothing but x-axis. Okay, there are three operations performed based on the time axis. Time shifting of signals. The meaning is it going to be delayed the signal or advanced the signal. Time scaling of signals, compressed or expanded. Time reversal signal, this is meaning reflection or mirror image. So these three operations are performed only depend on the x-axis, no change in the y-axis. Is it clear? First we can see time shifting of signals. Time shifting is mathematically expressed as y of t is equal to x of t minus k. K is the time shift and it is a constant. If k is positive, right shift or delay by k units. If k is negative, left shift or advance by k units. You take signal. The signal is x of t. You look at the signal. Okay. Here the k is 3. Clear? K is 3. If k is positive, right shift by 3 units. So the given signal, okay, shift towards right by 3 times. Okay, that is this part. Right shift is also known as delayed by 3 units. Now you come to the next part. Here it is given x of t plus 4. What is the k value? Minus 4. Here the k is minus 4. So what it will happen? If k is negative, left shift by k units. Okay. Now the same signal shifted towards left by 4 times. Okay. This is for time shifting. Now this is another example, okay, for discrete time signal. The previous slide we can see for continuous. This is for time, how the time shifting is obtained in digital signal. You consider the discrete time signal. This is original signal. Okay. Here the k is equal to 2 units. If k is positive, the above signal shift right by 2 times or time delayed by 2 times. Now here the k value is minus 3. Okay. Now if k is negative, it must be left shift. Then it is advanced by 3 times. Okay. In the negative side. This is the discrete time signal time shifting operation. The next property is time scaling of signals. Time scaling of signals involves the modification of a periodicity of the signal, keeping its amplitude is constant. There is no change in the amplitude. It's mathematically expressed as y of t is equal to x of a into t. Here a is the scaling factor. A is scaling factor. Okay. A is scaling factor. If A is scaling factor, how the signal varies depending upon the A value, we will see now. Okay. If A is less than 1, the signal x of t is expanded. If A is greater than 1, the signal x of t is compressed. Okay, x of t is compressed. You consider a original signal x of t. This is continuous time signal. Okay, here the scaling factor is a 1 by 2. Okay, 1 by 2 is nothing but 0.5. Now here a is less than 1. So if a is less than 1 means the x of t is expanded. Okay, how many times? That is 0.5 times the signal is expanded. Okay, if you take the another example, this is a is 2. A is 2 is nothing but a is greater than 1. If a is greater than means the signal x of t is compressed. So you look at x2 of t, compare with the original signal, this signal is compressed. So from this we observed that if depending upon the a value, the signals are compressed and expanded. This is the discrete time example for time scaling. X of n, here n is 2, that is a is 2. A is 2 means is a greater than. Here what it is? It is n by 3. N by 3 is nothing but a is 1 by 3. It is less than 1. Okay, so less than 1 means it is expansion. Greater than 1 means it is compressed. The next one is time reversal of signal. So the vertical, about the vertical origin, okay, this is vertical axis. About this axis, the right-sided signals reflected in the left side, the left-sided signal reflected in the right side. So this is the concept behind the reflection time reversal. Okay, now y of t is mathematically represented y of t equal to x of minus t. So the minus is nothing but mirror image. Okay, so you look at the example. If I keep the mirror, this will be reflected here. Okay, and this will be reflected into this side. Okay, this is called a time reversal signal. So the same thing we have time reversal signal for the discrete time signal. Okay, if I keep one mirror at the center, vertical axis, okay, the right hand side get reflected in the left hand side, the left hand signal reflected in the right hand side. So you look at the waveform, this is called a time reversal or reflection. Now we can see a simple example combining all the three operations. For the signal x of t, signal is given here. Find 1 by 2 x of minus t by 3 minus 1. So in the given problem, 4 types of operations are obtained. First one, time shifting. Second one, time reversal. Third one, time scaling. The fourth one is amplitude scaling. Okay, so if you come to this part, what is k value? K value is 1. It's a positive value. Okay, k is 1. It is a positive value. So the given signal is right shift by 1 time. Okay, this is right shift by 1 time. Clear? Over. Now the next one, do the reversal process. So the reversal process, in this equation you consider only this minus. This is nothing but reversal or reflection. So what I told you about the origin, whole signals gets reflected. Okay, so what will happen if I keep the mirror? This whole signal gets reflected in the left side. So you will get time reversal operation. Then you perform the scaling operation. Here a is 1 by 3. So a is 1 by 3 means it is less than 1. So a is less than 1. A is less than 1 means we have a expanded signal. So you will get expanded version of the time scaled signal compared to the given input. Okay, so the next part, amplitude scaling. So that is the half present at the outside is called the amplitude scaling. Okay. So here A is 1 by 2. So 1 by 2, this will give changes in the y-axis. Okay, what will happen means the amplitude 2 gets reduced exactly half. So what you will get, it is 1. Okay, you look at the diagram here 2. If divided by 2, if I put here, I put divided by 2. So 1.5, similarly here. So this is called amplitude scaling. So amplitude scaling also known as attenuation of the given signal. So you compare the signal and the amplitude scaled signal. The amplitude is exactly half. Okay, thank you.